Hi, I'm Pschirer from Pixelligent Technologies, and today I'd like to tell you a little bit about our company and about our high refractive index materials for extended reality. Today we expect more and more from our mobile devices, both in terms of form factor and functionality. Rapid advances in display, waveguide, and sensor technologies are combining to offer new, fully immersive experiences. Backed by the adaptive learning power of AI, these extended reality devices will create entirely new experiences in our daily lives, while increasing productivity and safety at the workplace. The hardware required to create bright, extended reality visual content without diminishing the real-world background or to improve the sensor capabilities is driven by new innovative materials and especially how these materials interact with light. Pixelligent is a materials company based in Baltimore, Maryland. Our focus is on materials that have a unique interaction with light, where we can manipulate how light travels through materials by tuning a property called refractive index. Our core technology is our high refractive index metal oxide nanocrystals, which when formulated improve the optical performance in various applications. Our materials are used by industry leaders along the entire consumer electronic value chain. Today we focus on three main applications. The first is extended reality, where our nano-patterned high refractive index materials improve the brightness and the field of view in extended reality devices. For optics and sensors, we have our solvent-free materials, which can be micro-imprinted, again, to improve the sensing capabilities, for example, in 3D sensors. And last but not least, for OLED displays, we have developed inkjettable materials under our PixJet logo, which help to improve the efficiency and brightness of OLED displays. Our unique process is based on the bottom-up synthesis of nanocrystals from precursors and the capping of these crystals with ligands to create dispersions, and upon the addition of monomers, additives, and solvents, we can create customized formulations that upon patterning can result in nanometers size grating structures as seen here on the bottom right. Today we focus mainly on titania, zirconia, and core shell nanoparticles, but we have an additional portfolio of up to 25 other metal oxides in our pipeline that we are currently evaluating. So as mentioned, we offer three types of nanocrystals today: zirconia, titania, and core shell. Our world-class performance of these nanocrystals is defined by our uniform and controlled particle size from 10 to 20 nanometers in stable dispersions and formulations. The SEM images and the DLS curves on the right-hand side show very low polydispersity index, indicating tight size control. Furthermore, when formulated and coated into thin films, we have refractive indices between 1.7 and up to 2.0, with industry best transparency and lowest haze. We can adjust our formulations to be solvent-containing or solvent-free, depending on the requirements of the end application. Our materials have extremely long shelf life, even at room temperature, which is very important for customers. And based on the viscosity, we can control the film thickness and enhance our mechanical properties. So looking a little bit at the evolution of Pixelligent, we started with zirconia, which is a high refractive index, highly transparent, highly stable material. And we developed all of the chemistry that you saw on the last slide for this. We've scaled it up. And with the onset of extended reality, this really drove us to increase our refractive index to 1.8 or higher, which led us to introduce new PixClear materials such as hafnium oxide or titanium oxide, or even barium titanate, which is currently under development. Pix 3.0 has been a really important development for us, which has enabled us to form strong partnerships with leading consumer electronic companies all along the value chain. And what we realized before this is just developing a specialty component to a formulation, it's really difficult to understand exactly the end user requirements and how our materials are interacting with their substrates and with their processes. And by becoming a formulator and creating customized formulations such as PixJet for inkjet, or PixNIL for nano imprint, or even PixCore, which improves the UV stability. These are all things that came on the heels of switching over to becoming a formulations provider. And in our last iteration, Pixelligent 4.0, we moved to a more advanced R&D system, such as using AI platforms to accelerate our process of developing these new nanocrystals for display, extended reality, and a variety of other applications. So coming back to extended reality, optical combiners act to combine the virtual image with the real-world content. How these work, if you look on the bottom left-hand side, is light is inputted into the lens from a light engine or a projector through some gratings. This light is reflected due to internal reflection based upon the refractive index difference between air and the substrate throughout as it goes through the substrate, and then is outcoupled towards the eye. And this then gives the image of the virtual content being projected out in front of you in the real world. And these optical combiners, the best ones today, are based on diffractive technologies because these really provide the brightest, most accurate displays without compromising real-world vision. They can be accomplished, as you see here, with two different methods. The one is the surface relief grating, again, which has actual protrusions of physically structured gratings, whereas the volume holographic grating works on the principle that within the bulk of the material, high and low refractive index zones are created, which give you a very similar effect with some additional advantages for next generation devices. So the surface relief gratings can be produced by two methods. First is the nano imprint, and secondly is by actually using photolithography, and an etching process on inorganic materials can be used as well. The nano imprint technique offers a lot of advantages, and this is the technology that we as Pixelligent focus on, and that we believe a majority of the major industry players in the extended reality world are focusing on today. So on this slide, I'd like to show you two things. I think first of all is reiterating that we're doing this work with the leading tool and material companies in this industry. And this is very important because we want to have materials that are ready to drop in to existing tools for the various applications. And on the left-hand side, I'd like to call your attention to these TEM images. So we're often asked when we create nanocomposite materials, so our formulations are made up of nanocrystals, but also organic resins. So when you're patterning these materials and stamping them, do the nanocrystals actually disperse evenly throughout the structures and rise to the top of these structures, or are they all stuck at the bottom? And we're able to show here very clearly with these TEM images that our nanocrystals are very evenly dispersed throughout the structures, which is very important. That means you have the same refractive index throughout the entire waveguide, which is critical. And even what we call the residual layer between the structures here, if you zoom in, you see that this is made up of only 2 to 3 nanocrystals. So again, really amazing control of the particle size and of the dispersibility throughout the patterns. We're also able to replicate here with EVG slanted gratings, which are very important for next generation devices as they have the really the best diffractive efficiencies and lowest light loss. We have here very small 60 nanometer structures produced with SUS, and on the bottom here you can see also additional slanted gratings with EDX imaging showing the dispersion of the titania throughout these nano structures, and these are made using Optool stamp materials and NILT masters. In addition to highly accurate diffractive gratings, there are other requirements required to have excellent performance in extended reality waveguides. First and foremost, both the substrates and the grading material must be highly transparent. This is something that we enable with our small nanocrystals, again, leading to this high transparency and low haze. Additionally, having a low residual layer between the gratings, having excellent surface uniformity, this improves or reduces light leakage in these waveguides. And I think of foremost importance for high refractive index materials, both of the substrates and the diffractive gratings, is that the high index really enables a high field of view. And to give you an example what a high field of view looks like, if you look at this image here on the right-hand side, going from a 30 to a 50 to a 60-degree field of view gives you a much more immersive experience. If you could imagine, this being the image that you're looking at through your extended reality headset. So we talked a lot so far about, improving the optics, the patterning performance, which leads to improved external quantum efficiencies. But as the extended reality industry really approaches mass production, we want to have our materials ready as a drop-in solution. So this includes having resists with long shelf life, again at room temperature. We want to have a drop-in solution that doesn't require any engineering changes for our customers. As you can see here, the equipment on the right-hand side is quite expensive, and we do not expect that they're going to change any of these processes because of any special requirements for our materials. That includes having a broad process window. Our material has to work under all conditions with slightly different processes or tools. This is very important for customers. And also we care about sustainability and ensure that our materials are PFAS-free, as well as the stamp materials that we're working with in these processes. So one of the final steps towards mass adoption of extended reality is the product reliability, of course. Using these materials outside, we need to have good temperature and humidity stability, and especially UV reliability. And that's something that we focused on improving, especially for our titania formulations, with our award-winning PixCore technology, which actually takes a titania nanocrystal and passivates the surface from any photocatalytic effect by inserting a very thin zirconia shell onto this titania nanocrystal. Again, these are around 20 nanometers in size, and they're compatible again with different solvent systems. And you could see an example here on the bottom left-hand side of how the refractive index, as we go from titania to core shell, stays almost the same, but the degree of yellowing that occurs upon UV radiation is reduced by over 75%. And we have even more recent results here where this has been improved even further, but they were not ready for this presentation. But PixCore is really an exciting product where we're basing a lot of our future formulations for various applications on this technology. High-index materials are also critical for next-generation 3D sensors and 3D displays. 3D sensors work by structuring IR light, which reflects off of an object and is read then by a camera. This light can be structured using nanopatterned films in the case of a dot projector here on the top, or by using micropatterned solvent-free materials in the case of diffusers. Advantages of high refractive index materials for these types of applications first of all start with being able to reduce the structure height of these features, which makes the production process easier and improves the production yields. But more importantly, these micro lenses improve the wide angle sensing capabilities of sensors, such as automotive, when you implement high refractive index materials. And if you can imagine, if you have sensors inside of a car that are supposed to read the facial expressions, for example, of both the driver and the passenger, here you're really talking about close distances where you require wide-angle sensing capabilities. And I should mention also that these same type of microlens structures, or in this case lenticular lens structures, can be used to develop next-generation 3D displays as well. So last but not least, we have also created solvent-free inkjettable materials to improve the brightness and efficiency of OLED displays. Recently, inkjet printing has become more and more common in OLED manufacturing, and our drop-in solutions are designed to work with the installed tools. If you look at the right-hand side, you could imagine that the inkjetted high refractive index materials can be used to form a flat layer for certain architectures, or they can be used to design individual microlens structures to improve the performance of the individual OLED pixels. So these, by requirement, are solvent-free materials with a certain viscosity. The viscosity has to typically be less than 25 CP at room temperature. These are UV curable systems, as are all of our formulations. They have long pot life and excellent film uniformity. And our first material which we introduced to the market is a zirconia-based SFZ5, but we are now developing a PixCore version of this material with a higher refractive index of 1.7, and of course higher refractive index is advantageous for OLED and micro OLED applications, as these materials are based on high refractive index emissive materials. So in summary, we've shown that our high refractive index material portfolio can be tuned for various applications regarding refractive index. The viscosity can be changed, the reliability has been improved, and our materials are designed to work, with a broad process window in all existing tools. So we focus first and foremost on extended reality, where our materials really play the critical role of combining virtual and real-world images as optical combiners. Our materials are improving the performance of 3D sensors and 3D displays, as well as the brightness and efficiency of OLED displays with our PixJet materials. So if there's applications that you're interested to look at our materials or have any further questions, I invite you to visit us at pixelligent.com, and I thank you for your attention today.